Welcome back to Chemistry Theory. This will be the last video in the MS2.2 section. So I thought I'd go through the assignment to give you a few hints with some of the questions. Now, you would have done questions 1, 2, 3, and 4 because those all dealt with the dispersion forces section. So when I was done talking about the dispersion forces section, I got you to do those ones. So now, looking at dipole-dipole and hydrogen bonding, we should be able to answer number 5, A and B yourself. And, maybe a little bit of hint with B, because some of these structures you may not necessarily know how to draw. So this one you likely do carbon bonded to 3 H's and an F. So of course from experience you know that that would look something like this. We could figure out the number of valence charges, etc. But to keep it quick, it looks something like that, right? And this one here is a little tricky. So you have carbon bonded to 3 H's. And then it's bonded to an N. And then that N is further bonded to 2 H's. There would be a lone pair of electrons there. Methanol is very similar to that previous one. Carbon bonded to 3 H's, an O and an H, and there would be 2 bonds. This shape right here would be a bent shape. Then over here, there we go. So those are the structures. And of course, what atoms must hydrogen be bonded to in a molecule in order for hydrogen bonding to take effect? So of course, we remember H must be bonded to an F, O, or N. Fon. Hydrogen bonding is fon. So that's what we have to take a look here. Do we have H bonded? So over here, which of the following would have can form hydrogen bonds with other of the same type? So in other words, if I had a container full of this molecule, would hydrogen bonding happen? Let's see, do I have H bonded to an F, O, or N? No, I do have F and I do have N, H, but they're not bonded to each other. This one? Yes, I would. I have H bonded to an N, so yes, hydrogen bonding would happen there. Over here, H bonded to an O, so yes. Then over here, H bonded to no, I don't. So I don't have it there. All right. Question 6 you should be able to do. Just simply looking at comparing the 3 major dispersion forces. And looking at number 7, you should be able to draw that out and then figure out what types of forces are involved there. I'm going to do the same thing with this one. This one is a little bit tricky. It's a larger molecule, it's organic, so we'll go through this one. So of course here we have 1, 2. There's 2 C's. 3 plus 1 is 4 H's, and then 2 oxygens. So carbon has 4 valence electrons, H has 1, oxygen has 6. So of course here we're going to have 24 valence electrons. Now how this order is set up kind of tells you how these atoms are joined together. Except that here it's a carboxylic acid area, and that one you likely don't know at this point. It actually looks like that with 2 lone pairs here. So if we count up these electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And if I was to do the formal charge calculation around the whole molecule, we would in fact see that that is the correct structure. So of course everything has dispersion forces. Okay, and the next would be check for dipole-dipole. Now it'd have to be polar. Now this area here would be non-polar. Basically carbons bonded to H's kind of below that 0.4 fringe region. So we know that would not be polar, but yes, we would have some polarity over there, so it would be dipole-dipole. There would be polar regions there if we look at our table of electronegativity. And in particular, we do have H bonded to an O, so we would have hydrogen bonding forces as well. So this has all 3. dispersion forces, dipole-dipole forces, and hydrogen bonding forces. Okay, should be able to do A and B though. Number 8, I'll give you a little bit of a hint with this one. We'll sketch it out. This is one we talked about earlier, actually, methanol. Then we have another one here. It looks very similar, very similar. So these are the structures here. So if we look at carbon, again, as I mentioned, carbon and H. So carbon has an electronegativity of 2.55. H is 2.2. So that, subtract that, I'm going to get 0.35. So yes, virtually non-polar. So there's a non-polar section there. What about C and O? C and O, that will be polar. 3.44 subtract 0.255 will be greater than the 0.4. So that's going to be a polar bond over here. And over here, S and C, 2.58, 2.55. So that is going to be non-polar. So that kind of tells you the answer right there. But we could continue here, and we know we have, oh yes, hydrogen bonding. And whereas here, H and S, so S is 2.58, H is 2.2, it's like 0.38, so almost non-polar as well, very close to that fringe number. So it says here, what type of intermolecular force accounts for each of these differences? So they both have dispersion, because everything does. Everything has electrons that could randomly move around. Dipole, dipole. And this one, yeah, virtually, so dipole, dipole, if we did have it, it would be very, very, very weak. Here we have hydrogen bonding. Oops, I forgot the R there. Hydrogen bonding. And then no hydrogen bonding. So yes, we can see here, so this should have, if I had a bottle of these types of molecules versus a bottle of these types of molecules, these would be held very close to each other, very strongly, because they have dispersion forces, dipole, dipole, and hydrogen bonding. And if we take a look at this boils at 65 degrees, whereas this boils at 6. We don't need that much energy to boil this. So that's because this has stronger forces, and of course, what's the big force that has to do with that? The hydrogen bonding force, because this doesn't even have it. This also has a stronger dipole-dipole force than this one. But yeah, the hydrogen bonding one is the big one that suggests that this one is going to be more difficult to boil or melt, more stronger dispersion forces there. Right, and the rest of the sum, you should be able to do this just looking at xenon versus argon. And these, yes, we have these structures. You should be able to draw these and come up with the reason as to why one has a higher boiling point. Again, higher boiling point implies greater forces of attraction to overcome. And then number 10, comparing H2o and H2s, you should be able to find a reason for that. It continues on to the next page as well. So you should be able to do all those, and if you run into a snag, just check the answer key for a little bit of a hint here or there, and you should be okay. All right, we'll see you again.